Hi, welcome back to my YouTube channel. In this video we're going to see how we should solve this integral of from 0 to 1 of negative 1 to the power of x dx, integrating with respect to x. So you might think about integrating this with traditional ways, but there is a better way to do it, and that is using Euler's formula. So I'm going to write the Euler's formula here. E to the ix is cosine x plus I sine x, which extends the trigonometry to complex functions. Now, I have proved this formula with Taylor series and Taylor expansion in my other videos. You can go and watch it in my channel. I'm gonna probably put it in the description so you don't have to search through all of my channel's content. But just so you know, I've also proved this formula. So what should we do now? So if you've watched my video on how we should calculate the ln of -1, you probably know that we should use this formula to relate e to the power of something to -1. And in this case, we're going to say e to the power of I pi. But is pi really enough? Does it capture the full numbers that it can be? No. So we're going to say pi plus 2 pi k, because if k is integer, if k is integer, our result is going to be 3 pi, 0 or 2 pi or 3 pi or 4 pi or 5 pi or n, etc. And when our result is like that, our cosine is going to be -1 and our sine is going to go away. So it's going to be -1 e of the I pi plus 2 pi k. Now I'm going to substitute this value here, and it's going to yield me e to the power of I times pi plus 2 pi k dx. 0 to 1 of this integral. So what is this integral of this? We can use the reverse power rule, the exponent rule for the e to the x function, and it's going to be, it's going to be 1 over I times pi plus 2 pi k times e to the power of I times pi plus 2 pi k x from 0 to 1. I forgot to place x here. Now I'm going to place it. So if I calculate this following integral, the 1 times I times pi plus 2 pi k is going to stay here. And when I subtract e to the power of 1 of this whole expression here minus e to the power of 0, I'm going to get e to the 1 times pi plus 2 pi k minus e to the power of 0, which is 1. 1 over I times pi plus 2 pi k times e to the I times pi plus 2 pi k. So now, in this expression, if I take a closer look at the e to the power of I times pi plus 2 pi k, I'm going to see that this is exactly equal to my Euler's formula, and this expression is equal to -1. Oops, I forgot to place -1 here, so this thing should be subtracted from 1 like this. And if I plug in -1 for this one here, because we stated that our formula explicitly here, it's going to be 1 over I times pi plus 2 pi k times e to the I times pi plus 2 pi. Oops, I should have written -1 instead of it. It was -1 minus 1. Now it's going to be 1 over I times pi plus 2 pi k multiplied by -2, which is -2 over I times pi plus 2 pi k. We're not done yet. If I multiply both sides by an imaginary number, I'm going to get -2i times I squared times pi plus 2 pi k. We know that imaginary numbers have a property that I squared is negative 1, where I is the square root of negative 1. Now, it's gonna be negative 2i times divided by negative 1 times pi plus 2 pi k. Let me create more space here. So these two negatives are going to cancel out, and I'm going to be left with 2i divided by pi plus 2 pi k. And I can factor out pi here. Pi times 1 plus 2k, where k is an integer. So now I can write my whole integral from 0 to 1. Just want to state a conclusion of negative 1 to the power of x dx is 2i over pi times 1 plus 2k. K is integer. K is an integer, and that is the true real power of the complex functions and complex numbers, that how they can solve the impossible for us. So hope you enjoyed this video. If you did, please like and subscribe, and I'll see you next video.